The physics concepts behind roller coasters, as presented to you by Brady Burns and Kelly Conlon.
In this slideshow, we will review and further explore several physics concepts we have covered this year and address their application and utility in respect to roller coasters. The main concepts we will cover today are conservation of energy, gravitational and inertial forces, as well as centripetal acceleration. This slide contains three important formulas for the topics that we will be discussing for the remainder of this presentation. The first formula seen in the image on the right is for conservation of energy. As you can see, the energy of the system at the beginning must be equal to the energy of the system at the end. This means that the kinetic plus the potential energy at the beginning must be equal to the kinetic plus the potential energy at the end. The second formula is gravitational and inertial masses. As you can see, inertial mass is equal to mass times acceleration, whereas gravitational mass is equal to the mass of one object times the mass of a second object divided by the radius of the larger object. The third formula is for centripetal acceleration. This formula states that centripetal acceleration is equal to the velocity squared divided by the radius.
The first topic we will consider today is conservation of energy. As many of you know, conservation of energy states that the total energy of an isolated system remains constant. The law states that energy can neither be created nor destroyed. This concept can be applied to all types of energy. As seen by the picture in the bottom right corner, energy transformations occur across many different types and are always conserved in their environment. For our purposes of applying conservation of energy to roller coasters, however, we will be looking largely at the transformation and conservation of energy from kinetic and potential. This concept is not important solely in roller coasters, but also in biking up hills, as seen in the picture in the bottom right corner, as well as in freefall motion.
As mentioned in the previous slide, the main conversion of energy in roller coasters is between kinetic energy and potential. However, there are additional energy types and fluctuations at play. The climb up the hill requires electrical energy. As the roller coaster gains more and more height, the potential energy rises in proportion with the electrical energy's losses. Another factor to be considered is air resistance. Air resistance manipulates mechanical energy so that it is not truly conserved. Engineers know this, so they design roller coasters with each subsequent hill shorter than the first. By doing this, engineers avoid having to use a motor again in slowing down the ride. The ride is kept at high speeds without pause, as Americans love, due to engineers' understanding and manipulation of conservation of energy.
The second topic we're going to consider is gravitational and inertial forces. As a reminder, inertia is the tendency of an object at rest to stay at rest, and gravitational forces are the force between any two objects with mass. However, this attraction is only significant when an object has a very large mass, such as the Earth or Sun. Gravitational forces are present throughout the entire planet, playing a role in things as simple as an apple falling from a tree, as seen below, and as complex as humans building muscle through resisting gravity. Another time that gravity plays a significant role is in freefall. In roller coasters, this can produce a feeling of weightlessness in the rider. Inertial forces can be seen clearly in the picture below. Inertia is a major contributor to the unusual feeling produced in a rider, as we will take a look at in a moment.
Gravitational and inertial forces work together to make a rider feel both heavy and light as they travel along a roller coaster. Although most roller coasters require a seatbelt, many times, gravitational and inertial forces balance each other out on vertical loops so that a seatbelt is unnecessary for the majority of the ride. G-forces, the commonly used term for gravitational acceleration, vary throughout a ride. A person standing still on the surface of Earth experiences 1 g, or an acceleration of 9.8. As a roller coaster progresses along its track, a rider may gain a sense of weightlessness as the roller coaster travels down a free fall. This feeling of weightlessness is due to the negative g's experienced by the rider as they travel down the free falls of a track.
The final topic we will explore and apply today is centripetal acceleration. Centripetal acceleration is the rate of change of tangential acceleration, but simplified, it's simply when an object moves faster or slower in a circle. Centripetal acceleration occurs when an object is rotated in a circle and either speeds up or slows down. A time when centripetal acceleration is necessary to be considered is on a racetrack, as seen below. Racers need to balance their speed so that they go as fast as possible without losing control over their vehicles. To do this, racers must calculate the track's friction and angle. Knowledge of centripetal forces and acceleration is also utilized for civilian drivers by engineers who calculate these values to post a safe speed at which drivers are advised to stay under when taking a turn. Centripetal acceleration is also an important component in Ferris wheel and carousel safety, as engineers must take care to stop and start the ride with a speed that results in minimal rocking and does not disrupt the structural integrity. Centripetal acceleration is essential to roller coasters loops, as we will find in the following slide.
In regards to roller coasters, centripetal acceleration is most notable on clothoid loops. A clothoid loop is a loop where the radius is much larger at the top of the circle than it is at the bottom. The centripetal acceleration of the rider changes in speed as well as direction as the rider travels along the clothoid loop. These loops are utilized because if each loop on a roller coaster were a perfect circle, the roller coaster would never be able to operate successfully. Due to conservation of energy, the higher the cart travels up the loop, the slower the cart moves. This is because as the riders gain height, they also gain potential energy. These increases in potential energy also result in a decreased kinetic energy. The opposite is true as the rider comes down the loop, and as height and potential energy decrease, the rider's kinetic energy and therefore speed increases. This increase in kinetic energy causes the rider to have a maximum speed when entering and leaving the loop.
Over the years, numerous physics concepts have been applied to make roller coasters more extreme while also becoming more safe. In 1888, the first looping roller coaster, Flip Flap Railway, was instated. The small diameter of the circular loop meant that the force on riders was approximately 12 Gs. Because of the force of its design, riders often experienced extreme discomfort and occasionally even whiplash. The lesson learned from this coaster was never to use a truly circular loop. Another major innovation was under-friction wheels by John Miller in 1919. These wheels kept the coaster on the track through intense movement or loops. These wheels made it possible for engineers to create crazier tracks by fighting against gravity while keeping riders safe.
This slide contains all of our citations for all images used and presented in the slides. We hope you enjoyed learning about conservation of energy, gravitational and inertial forces, and centripetal acceleration's influence on roller coasters and their motion.